So let's discuss another manifold learning technique. We will focus on locally linear embedding. This algorithm has been proposed for more than 20 years ago. So you can look at it. The original paper was published in Science back in 2000. And this is what I checked before, back in 2019. It has been already cited by 13,000 times. And even if you go to ResearchGate, it has been cited by almost 7,000 times. So this is a very, very well cited paper, and technically almost the first nonlinear dimension reduction algorithm. However, how much do we know about it? If you look at the previous claim back in 2003, it says that it is close to graph Laplacian. And people took it, which is okay, because later on you will see it does look like graph Laplacian, but it is more complicated by close to. It contains a lot of intrinsic structures that we can explore. So that is the topic we want to talk about in this series of lectures. So first, let's recall the algorithm, locally linear embedding algorithm. So what is locally linear embedding algorithm? First, you will have a set of points in a p-dimensional space. Let's call it x1 up to xn. Then what you do is, first, for every point I, you can find all neighbors, called ni. Those are the points that are within the distance less than epsilon within from xi. So this is called epsilon ball scheme. You can also consider k nearest neighbor scheme. Then you evaluate barycentric coordinate. Barycentric coordinate. You have wi. Okay. What you do is you try to find arcmean of the weight w, and w is in n-dimensional space. This n, capital N, is a number of points in a neighbor of point xi. And you want this omega, this vector, to have the weight 1. That is, if you sum everything, it becomes 1. And then you say, hey, we view xij as a basis, okay, and you do some kind of combination, okay, then you get xi. That is this is the intuition of barycentric coordinate. Okay, you view xij as kind of the basis or something, and you do some combination, which will approximate xi as well as possible. Which then you can rewrite it as xij minus xi, because you know w transpose 1 is 1. So you can just put xi here and rewrite wj outside. That is what you have. And when you do the arcmean here, you can rewrite this guy as G times W, where G is the local data matrix. So you can understand this as you have all the neighboring points compared with xi, and you take all this and you try to find some weight W so that this G is as close as possible to 0. That is what you are doing, barycentric coordinate. So this is the main step. You try to catch the geometric information. And you have this geometric picture of this mathematical formula. You have xi, and you find all the neighbors, okay? And you try to use the relationship in between all the neighbors and the center point, and you determine some weight, so that you see a relationship in between neighboring points and the xi. That is the geometric information we try to capture. And then, how to solve this minimizer? How to solve this optimization problem? We just consider Lagrangian multiplier so that you get Wi is G transpose G inverse times 1 divided by it. But in practice, G transpose G might be degenerate, so that you cannot take inverse. So you just replace G transpose G by G transpose G times plus some constant C. This C is the regularizer, which plays a fundamental role in locally linear embedding. So remember the C, which will come back in a bit. And this will be the key part that we'll discuss. So once you replace G transpose G inverse by G transpose G plus C inverse, then you get the final algorithm. You get Wij, so you get Wi, K, okay, which comes from this replacement. Now what we do is we want to construct a big matrix called W, which is an n by n matrix. And how to fill in the n by n matrix? We consider the ith entry, ith row. Okay, and in the ith row, what we do is we will plug in Wij, the j's entry to be Wi of k, if the j's point, this j's point is actually the k's neighbor of xi. Okay, so for the ith point, you will have I1, the first neighbor, second neighbor, third neighbor. Okay, and for these three neighbors, we will plug in just Wi. Wi is evaluated by Lagrangian multiplier with regularizer, and you put the first entry here, second entry here, third entry here. Okay, so this is a W. And you can see that W is what? W turns out to be something very similar to the affinity matrix. Why? Because all the rows will sum up to 1. So it's like affinity matrix. The only thing that we are not sure is, will all the entries be positive? If all the entries are positive, then this is something just like what we considered back in graph Laplacian, because all the entries are positive, so you have the random walk interpretation. But here we may not have the random walk interpretation. And we will see under some conditions, we do have random walk interpretation. But in some cases, we may not. Okay, so now we have affinity matrix. Then what you can do is, you can just evaluate its singular value decomposition. And remember, because this matrix does not guarantee to have some structures, so it may not have eigenvalue decomposition. Just like when we run KNN construction of graph Laplacian for diffusion map. If it is, in general, KNN neighbors, then eigenvalue decomposition of the graph Laplacian may not exist. And here, we consider singular value decomposition because, in practice, what we do is we have to have W transpose, we symmetrize it, and then evaluate eigenvalue decomposition. That is usually what is implemented in local linear embedding, which is equivalent to evaluate singular value decomposition of W. Okay, and we call W the LLE matrix. And that is what we want to analyze. Okay, and once you get singular value decomposition, you can run the embedding using the eigenvector, singular vectors and the singular values, just like what we did in graph Laplacian diffusion maps and so on. So this is the algorithm. Very simple, very intuitive, and it has been applied in many problems under the first nonlinear embedding algorithm. So again, this is a key ingredient of local linear embedding, C, regularizer. Keep it. So we want to see how does this algorithm captures the nonlinear geometry. What do we have? What do we do? So we need to play with this matrix and do something. So you have G transpose G, and this matrix may ring a bell, right? This is very much like the gray matrix of the data set, right? So what you can do is you have G transpose G, and it has eigenvalue decomposition. So you have eigenvalue decomposition, which is V lambda V transpose, and you just plug it in. And you have V lambda plus Ci inverse V transpose 1. Okay? Now, you can just do the expansion and get C inverse 1 plus V lambda plus Ci inverse minus C inverse I V transpose 1. That will be the expansion we will count on. Very simple expansion. So what you can see is with this formula, the Wi or the affinity looks like this guy. And if you pay attention, what do you see? You see this is a vector, right? And what is in the denominator? This denominator is nothing but you sum all the entries in the numerator, right? That is, you take the numerator and you multiply it by 1. So if you multiply this guy by 1, you put 1 on the right hand side, you do multiplication. 1 transpose 1 is n, because there are n neighbors. And 1 transpose V, this block becomes 1 transpose V, bracket, V transpose 1. So this looks like what? This looks like normalization, isn't it? That is why Wi transpose, the affinity we get, is actually looks like a normalization step in graph Laplacian construction. So you can see here, G transpose G is a grand matrix, and the G transpose is covariance. And the G transpose and the G transpose G, they are related. Simply, you see, if you have the covariance matrix, which is U lambda tilde U transpose, and you have V, which is the eigenvalue decomposition of G transpose, this is transpose G, then V, if you take the first R eigenvectors, then it is related to Un with a pseudo inverse of the singular values. So you can get the relationship in between V is here, and the U here, via the G matrix itself, but you do some restriction with some pseudo inverse. And this is a Penrose-Moore pseudo inverse, where you put R, which is the rank of G transpose G, and the rank of G transpose G is the same as the rank of GG transpose, and this J NR is nothing but you take of this N by R matrix with O1 on the top, R by R matrix, and all the others are 0. So you have this this kind of a trivial relationship to link the single eigenvalues of GG transpose, eigenvectors of the Gram matrix and the eigenvectors of the covariance matrix. And if you take this relationship into account, then you can plug in everything. You can replace V by G transpose U, and this is lambda tilde pseudo inverse 1/2, and so on. You plug everything. And now you do some calculation, you see lambda 1 minus half times C divided by lambda plus C minus 1, lambda minus 1/2 is 1 over lambda plus C. by taking this into account, then this block, if you do a simplification, it is reduced to this guy. And what is it? This JPR transpose, this is a projection, right? So what do you get? You get 1 here, 1 here, G transpose. But here you have GG transpose covariance matrix, but you do some regularization. Regularization, which is related to 1 plus lambda plus 1 over lambda plus C, and the G is here. And this is related to what? This is related to pseudo inverse when C goes to 0. So here, what we are doing is doing some regularizer, so that we can take inverse. And this IC is a regularized pseudo inverse. So technically, in the end, what we are doing is we are doing some kind of pseudo inverse, but we do some regularization. And this regularization comes from the barycentric coordinate. And we use this regularizer in a barycentric coordinate, somehow is related, and you do some simplification to get the pseudo inverse of the local covariance matrix. This GG transpose, we will spend some time on it in a later lecture. It actually captures the local tangent, it actually estimates the tangent space if we are under the manifold structure. And this local covariance matrix has a lot of, encodes a lot of geometric information. So, this is a kind of a direct rewriting of the original formula, which is technically trivial, but it leads to a more understanding of the geometry. Again, this GG transpose encodes the tangent space information. So what we are doing is actually capturing the curvature. As we will see later, this actually captures the curvature. Okay, so once we can this rewriting, Wi becomes this formula. And we somehow get the notion called kernel. We call it LLE kernel. And what is a kernel? This is actually a kernel. This is a kernel. If you forget about the second part, you just forget about the second part. Forget about this part. You have one transpose. This is what? This is a 0-1 kernel. This is 0-1 kernel. That is, you assign 1 to all the neighbors. This is 0-1 kernel. But right now, you do some correction. This correction depends on the local covariance matrix and do some regularized inverse. And when you have Vi transpose V, Wi transpose V, this is what you get. And if you pay attention, what are you doing? You are kind of distributing V according to some probability if Wi is a non-negative vector, right? Because you can understand Wi as a probability of the associated random walk. Okay, overall, again, it's not easy to see its behavior. For example, is it really positive? Are you sure? Right? It's not easy to guarantee this kernel will be positive. So how can you say it is really something like you are really doing some kind of a good random walk, right? You cannot. And this is an example which tells you actually, depending on how you choose C, you may have different behaviors of W. And we'll come back to this plot later. These three, black one, you can see there's a blue one and the red one. Okay, they come from different normalizations. So the behavior of Wi can be very different. So in the end, what we say is we call this guy is kernel, G transpose. And remember what is kernel? It is G transpose, right? And you have this guy. And what we say is, oh, let's call 1 minus G transpose T. This T is this guy. We call this guy the augmented vector. Augmented vector. Because it will help you to see something like how you augment the local information. So we call this augmented vector. Okay, so this is inverse, which emphasizes the normal bundle direction. And this, again, will emphasize normal bundle correction. So somehow, although we are trying to get the tangent space covariance matrix, but actually what we are doing is here is trying to emphasize the normal direction. Okay, and this will be when we discuss the local covariance matrix and tangent space estimation later, you will see more. And there are some kind of interesting problem which is kind of relatively open. We don't know what's going on. For example, this is the distribution of the eigenvalues of the LLE matrix when the data is sampled randomly without any manifold. Just random noise, random Gaussian noise. And you run LLE and you get a LLE matrix, which is non-symmetric. You get complex eigenvalues paired, then you can see some kind of beautiful plot, which seems to have some specific structure, but nobody knows what's going on. And if you have different values, different pairs, you can see the eigenvalue distributions seem to have some interesting geometric plot. And interesting enough, you can always see here, 1, 1, 1, 1, 1. Okay, so this is kind of interesting behavior. Okay, so we'll discuss the manifold model a bit, but it will not be the focus today. But I want you to see some manifold model we will use in the later lecture to understand LLE. And the manifold model is exactly the same as what we do when we analyze diffusion maps. So it should be relatively simple if you have seen the diffusion map 1. So the assumption is always like, oh, X is a p-dimensional random vector, okay, and its range is supported on a d-dimensional manifold embedded in Rp, and we will assume manifold is compact, and in the beginning we will assume the boundary is empty, but later on we will also consider when boundary is non-empty, and you will see that when boundary is non-empty, we have a lot of interesting behavior of LLE. For example, the random walk, the W matrix will no longer be a random walk, and the boundary condition is so far still unknown. And you have a manifold, Riemannian manifold. The matrix is induced from the ambient space, and this is how it looks like. You have a random vector mapped to MD, and you get the induced major, a manifold, a Manifold set, and then you make the assumption that the induced major is absolutely continuous, so that you can have a density function, and you assume the density function is always non-zero, and it is C5. And this is the kind of the main difference compared with diffusion map analysis. We need C5 because in general, we do not know how to choose the regularizer. And you will see later, when you want to understand the regularizer, you need to do Taylor expansion many times so that we can fully understand what's going on. That's why we need C5. And this is the embedding, the pictorial picture of the embedding. Omega is the event space, X is a random vector, this is embedded manifold, this is embedded. Okay, and this is another picture of what we have shown in the previous slide. Okay, and this is what we have. And now we have the sampling scheme. The sampling scheme is we have X random vector. Now you just IID sampled n points, okay, on the manifold, and you have a function which is continuous on the manifold, so you can construct a discretization of the function on this n points, which becomes an n-dimensional vector. Okay, so that is IID sample. So in a continuous setup, what we expect will be first, you have 1 over n GI, G1, and what is this guy? What is this guy? What is this guy? So let's take a quick look. This is what we have. Uh-oh. This is here. We have several terms, right? 1 transpose n, and the G1 transpose, and all these terms. Okay, and all these terms turns out can be analyzed. And we would expect them to have the following behavior. First, 1 over n G1, it can be written discretizely in this way. And when n goes to infinity, we expect that it will converge to this form, this expectation. Okay, and we need to do some analysis and to see how fast, how this quantity converges to the expectation. And we also have this pseudo inverse, regularized pseudo inverse. How does it converges to CI? Remember this guy 1 over n GG transpose. This is a covariance matrix, local covariance matrix. And this is a local covariance matrix in a continuous setup. And the capital N divided by n will be converges to another random vector, which is supported on ambient space dimension ball centered at x of radius epsilon. That is what we expect. We will do some variance analysis, which is by large deviation, which is standard and almost the same as the graph Laplacian, but depends on C in a tedious way. And we will show the result in the next lecture. And similarly, in a continuous setup, we will have augmented vector, which, remember, this is what we want. When it goes to infinity, we have Ti, which looks like pseudo inverse of the covariance matrix, and times this vector, and so that the Wi transpose F hat will converge to this guy. And you will see that this guy actually is a kernel, which is related to some kernel defined on the manifold for some function. And this is how the augmented vector looks like. And this picture shows you on the left-hand side, when you have boundary, then you can see augmented vectors will have very peculiar behavior. And away from the boundary, you can see they have some very interesting behavior, which we will take a closer look in the future, in the next lecture, okay? And yeah, this is actually for this lecture. And there are 3 papers in this direction, trying to study locally linear embedding, and we will go through some topics discussing these papers in the coming lectures. We'll continue it.